Imagine holding a message from the early universe in your hands, a message older than the sun, older than the Earth itself, carried across the galaxy for billions of years, finally arriving in our solar system for us to read. On March 6, 2026, a paper was submitted to Nature, the most prestigious scientific journal on Earth. This wasn't a preprint, it wasn't presented at a conference. It was a formal, peer-reviewed revelation. The authors? Scientists from NASA's Goddard Space Flight Center. The instrument? The James Webb Space Telescope. The finding? Absolutely unprecedented. The water inside the interstellar object 3I, Atlas, contains 10 times more deuterium than any comet ever measured in our solar system. 10 times. Not a rounding error, not an instrument artifact, a discovery 12 sigma above the mean of all known protostars in the Milky Way. For context, the only object in our solar system with a comparable deuterium ratio is Venus, and Venus got there through 4 billion years of atmospheric escape, losing its light hydrogen to space while the heavy hydrogen stayed behind. 3I Atlas has no atmosphere. It didn't lose its hydrogen. It is a 2.6 kilometer ball of ice and rock, drifting through interstellar space for longer than Earth has existed. The paper points to a chilling truth. This object formed at temperatures below 30 Kelvin, in a stellar system poor in heavy elements, 10 to 12 billion years ago. That's before our sun, before our solar system, even existed. To grasp the significance, we need to understand deuterium. Hydrogen, the simplest atom, has one proton and one electron. It's the most abundant element in the universe, forming the backbone of stars, water, and life itself. Deuterium is hydrogen's heavier sibling. It has one proton, one electron, and one neutron, making it twice as heavy as normal hydrogen. The primordial universe set a fixed ratio. About 1 in 40,000 hydrogen atoms is deuterium. Stars gradually destroy it over billions of years, fusing it alongside regular hydrogen. In comets from our solar system, the deuterium to hydrogen (DH) ratio in water ranges from 0.03% to 0.06%, slightly enriched compared to Earth's oceans, but well within expectations. But 3I Atlas shatters that expectation. On December 22, 2025, Webb measured its DH ratio at 0.95%, nearly 1%. Compare that to our comets, 0.03%, 0.06%. Compare it to Earth's oceans, 0.016%. Compare it to the mean of all protostars in the Milky Way, 0.1%. 3I Atlas is 12 standard deviations above the galactic mean. This isn't slightly unusual, it's extraordinary. The object's water preserves a chemical memory of conditions in the early Milky Way, in a region colder and older than anything our solar system has experienced. What does this mean for temperature and formation? Cold chemistry dictates deuterium enrichment. The colder the environment, the more deuterium substitutes into water ice. For context, comets with a DH ratio around 0.05% formed at 2030 Kelvin. But 3I Atlas, with its DH ratio near 1%, formed below 30 Kelvin, likely in the even colder regime where carbon monoxide freezes. Not in a protostellar disk like our solar system's planets, but in a dense prestellar core, in the molecular cloud that would eventually form stars. This is the coldest phase of star formation, with temperatures of 1020 Kelvin and timescales of hundreds of thousands to millions of years. The ice in 3I Atlas preserves a record of those conditions, unaltered for billions of years, traveling through interstellar space until it sublimated near our sun and revealed its secrets. And it's not just the DH ratio. Carbon isotopes add another layer of cosmic history. The ratio of 12C to 13C is a clock for galactic chemical evolution. The more 13C, the more generations of stars have lived and died, enriching the interstellar medium. 3I Atlas has ratios far higher than solar system comets or nearby molecular clouds, pointing to a formation in a galaxy that had barely begun producing heavy elements, a metal-poor, ancient environment over 10 billion years ago. This is the opening of a story few could have imagined, a tiny icy traveler delivering a chemical message from the Milky Way's youth, and we are just beginning to decode it. What does it mean that 3I, Atlas formed in a metal-poor environment? In astronomy, metals aren't just iron and gold, they're everything heavier than helium, carbon, nitrogen, oxygen, silicon, iron, and so on. The universe began almost entirely with hydrogen and helium. Every atom heavier than that was forged in the hearts of stars and released when those stars ended their lives. The first generation of stars had essentially no metals. Each subsequent generation formed from gas enriched by the deaths of the previous stars. A metal-poor environment, like the 1-3I, Atlas came from, experienced relatively few generations of stellar birth and death. It's a direct snapshot of the early universe, a region of the Milky Way that existed when heavy elements were still scarce. This has profound consequences for chemistry. Less silicon, less iron, less carbon relative to hydrogen means different dust grain composition, different catalytic surfaces for ice chemistry, and a different efficiency for forming organic molecules. In other words, 3I, Atlas isn't just chemically distinct because it's from another star system, it's chemically distinct because it's from another era of the Milky Way. Its methanol enrichment, measured at 8% of total vapor 4 times higher than the solar system average, suddenly makes sense in this context. The isotopic fingerprint aligns perfectly with a cold, metal-poor formation environment from over 10 billion years ago. The implications extend even further. Scientists spent 8 months measuring the outgassing of 3I, Atlas, tracking methanol, HCN, CO2, OCS, methane, and water production rates. These observations come from the outer layers of the nucleus, heated by the sun's radiation during its solar passage. But isotopes go deeper. They reveal intrinsic fingerprints of the molecules themselves, unaffected by heating or outgassing. The DH ratio in water ice and 12C, 13C in CO and CO2 are encoded at formation and preserved over billions of years. This means 3I. Atlas is not merely a comet from another star system, it's a physical sample of the early Milky Way, a messenger delivering data about a molecular cloud that existed before our solar system ever formed. We cannot observe a molecular cloud from 10 billion years ago directly. We can infer early galactic chemistry from stellar spectra, meteorites, and theoretical models. But 3I, Atlas gives us a direct, measurable sample, preserving its isotopic signature across an interstellar journey that spans time itself. On December 22, 2025, the James Webb Space Telescope captured the DH ratio in water vapor released by this 1.0 billion year old planetesimal. That measurement, 0.95% deuterium, didn't exist in human knowledge before that day. It resolves questions about age, confirming that 3I, Atlas is older than our Sun and Earth, and opens new questions about its parent stellar system, ejected billions of years ago into the early Milky Way. We may never know the exact stellar system that birthed it. Its trajectory has been scrambled over billions of years by galactic rotation and mixing. But we know broadly, it came from an old, low metallicity environment, likely in the thick disk or early thin disk of the Milky Way. And this raises questions beyond age and origin. What about the organic molecules methanol, HCN released from 3I, Atlas? Were they enriched in heavy isotopes as well? If so, that has profound implications for prebiotic chemistry, for the kind of molecules that could seed life, and for the chemical pathways of amino acids and other complex organics. Deuterium-enriched precursors behave differently in polymerization reactions. These are processes that could fundamentally alter how life forms in different parts of the galaxy. 3I, Atlas is the first interstellar object for which such isotopic measurements were possible. It was bright enough, active enough, and observed with Webb's high spectral resolution during outgassing. Future interstellar visitors will be prioritized for isotopic measurements immediately before perihelion, ensuring that we capture the most pristine material before surface volatiles are depleted. This single object opens a new chapter in our understanding of galactic chemistry, early stellar evolution, and the chemical origins of life. Even as the comet passes, astronomers continue to refine their understanding. On March 12, 2026, just 4 days before its flyby of Jupiter, Avi Loeb published a Q&A updating his classification of 3I, Atlas. Previously rated 6 out of 10 on a scale, assessing potential alien technology based on 15 to 16 anomalies, including sideways jets, unexpected spin behavior, and orbital peculiarities. He revised it down to 3, acknowledging that the bulk of the object's behavior is consistent with natural cometary physics. Yet he introduced the Trojan horse hypothesis, suggesting that an interstellar civilization could, hypothetically, use a natural iceberg to carry technological payloads. It's critical to understand, this isn't a claim that 3I, Atlas is a spacecraft. It's a scientific framing of possibilities, illustrating the careful attention and curiosity of experts, observing something that defies conventional explanation. The story picks up on December 22, 2025, when the James Webb Space Telescope turned its gaze toward a 2.6-kilometer ball of ice, 3I, Atlas, and captured data that would rewrite our understanding of interstellar objects. By measuring the water vapor released from the comet's surface, Webb determined the DH ratio to be 0.95%. To put that in context, that's 10 times higher than any comet ever measured in our solar system. It's 12 standard deviations above the Milky Way mean, a clear and undeniable signal. This is not a minor anomaly or a calibration error. It's a precise, multi-instrument, independently confirmed measurement of the object's history, chemistry, and the environment in which it formed. The significance of this ratio goes far beyond numbers. In ordinary solar system comets, DH ratios in water range from 0.03% to 0.06%. Earth's oceans sit at 0.016%. 3I, Atlas, at nearly 1%, is in a category entirely its own. The DH ratio functions as a cosmic thermometer. The higher the ratio, the colder the environment where the ice formed. For comets in our system, ratios around 0.05% indicate formation temperatures between 20 and 30 Kelvin. But 3I, Atlas's water formed in temperatures below 30 Kelvin, possibly much colder, in conditions where even carbon monoxide would freeze. This is far colder than the outer regions of protoplanetary disks. It's the regime of dense molecular cloud cores, the very precursors to star formation. What this means is profound. The water ice in 3I, Atlas did not form around a young star or within a protostellar disk, like the one that birthed our solar system. It formed in the coldest prestellar cores, in dense clouds before any star had ignited nearby. This ice carries a chemical memory of the early Milky Way temperatures, densities, cosmic ray shielding, and environmental conditions that existed billions of years before the Earth ever formed. The very molecules that sustain life on our planet water here encode a history of the galaxy itself. The story doesn't end with water. Carbon isotopes provide a second independent clock. 3I Atlas exhibits extremely high 12C, 13C ratios, 140, 1 to 190, 1 for CO2 and 123 to 170, 2 for CO compared to 89 inches the solar system, and 60 to 80 inches nearby molecular clouds. Higher 12C, 13C means less 13C, indicating fewer generations of stars had enriched the environment. This confirms 3I, Atlas formed in a metal poor, early epoch of the Milky Way, 10 to 12 billion years ago, far older than our Sun, far older than the Earth. A second paper, published the same week by a team led by Shreel Opatam at Virginia Tech, measured nitrogen isotopes in CN molecules and found 14N, 15N ratios, more than twice those typical of solar system comets. 2 independent isotopic systems, 2 teams, 2 instruments, and the same conclusion. 3I, Atlas formed in the early Milky Way under low metallicity, extremely cold conditions. This is not speculation, it's measurement. It's direct evidence of the chemical state of the galaxy billions of years ago. By capturing these isotopic fingerprints, we gain a rare glimpse of interstellar chemistry preserved across cosmic time. Unlike ordinary cometary abundances, which can be altered by solar heating and outgassing, isotopes are locked in at formation. They survive the eons, making 3I, Atlas a true time capsule, carrying intact information from a galaxy we can never visit directly. The object has traveled billions of years, preserving a record of a pre-solar, low-metallicity environment that no longer exists. Even as 3I, Atlas continues its journey, these measurements answer some questions and open others. Its age is now firmly constrained, older than our Sun, older than our solar system, formed in a time when the Milky Way was young and chemically primitive. Its parent stellar system, long gone or untraceable, originated in the thick disk or early thin disk of the galaxy. But the presence of organic molecules like methanol and HCN raises a tantalizing question. Are these organics also enriched in heavy isotopes? If so, they could impact prebiotic chemistry in ways we've never observed, offering clues about how life could emerge in diverse interstellar environments. And the clock is ticking. On March 16, 2026, 3I, Atlas will pass Jupiter, accelerating towards Saturn, Uranus, Neptune, and finally into interstellar space forever. We have only a brief window to capture these unique measurements. The comet is an irreplaceable messenger, a sample of the early Milky Way delivered directly to our instruments. The chemical memory it carries is a treasure trove for understanding galactic evolution, stellar chemistry, and the origins of molecules essential to life. As 3I, Atlas approaches Jupiter, the scientific excitement is palpable. 4 days before the flyby, on March 12, 2026, Harvard astrophysicist Avi Loeb published a Q&A revising the object's rating on his classification scale from 6 down to 3. Earlier, in January, after the 120 jets were revealed by Hubble, Loeb had raised the score to 6 out of 10, with 0 representing a natural comet and 10 signaling confirmed alien technology. That higher score reflected anomalies, sideways motion from jets, the Hill sphere coincidence, and 15 to 16 other unusual characteristics. But with more data, including the physics of outgassing, the spin evolution, and orbital dynamics, the evidence leaned increasingly toward a natural explanation. Loeb did, however, introduce a concept he called the Trojan horse hypothesis. It's not that 3I, Atlas, is a spacecraft, but rather that it could be a natural iceberg with a passive payload installed by an interstellar civilization. The iceberg provides shielding, while its trajectory acts as a delivery system. He also raised a public question about whether 3I, Atlas, might release small probes during the Jupiter flyby, deployable objects that receive a velocity kick at the Hill sphere boundary, potentially entering gravitationally bound orbits around Jupiter. This is a hypothesis rooted in extreme scientific curiosity. It's not speculation for entertainment. Loeb has published over 900 peer-reviewed papers, and his questions deserve to be on the record. But the focus remains firmly on measurements. On December 22, 2025, Webb measured the ratio of heavy water to regular water in the gas released from this 2.6 kilometer ice ball. The result, 0.95% DH, confirmed a tenfold enrichment relative to any solar system comet. 12 sigma above the Milky Way mean. It confirms formation at temperatures below 30 Kelvin in a metal-poor stellar environment 10 to 12 billion years ago. That is a frozen record from an era that no longer exists. This data has been carefully calibrated, cross-checked, and peer-reviewed, then submitted to Nature on March 6, 2026. Yet, despite its significance, it initially went unnoticed in mainstream coverage. The world kept scrolling, unaware that in 4 days, 3I, Atlas would pass Jupiter, then accelerate outward, leaving the solar system forever. The window to study this object is closing, but the essential measurements have already been captured. Scientists now hold a direct isotopic fingerprint of the early Milky Way, preserved in ice delivered to our instruments by a visitor from the ancient galaxy. Every measurement carries weight. The DH ratio tells us the temperature at which the ice formed, pointing to the coldest phases of star formation in pre-stellar cores. Carbon isotopes, the second clock, reveal the galaxy's chemical evolution. Nitrogen isotopes from CN molecules, measured independently by a separate team, corroborate formation in a low metallicity environment. 2 teams, 2 isotopic systems, 2 instruments, all converging on the same conclusion. 3I, Atlas is a messenger carrying information from the early Milky Way, billions of years before our sun and planets existed. And yet, anomalies remain. Methanol enrichment in the comet's vapor is 4 times higher than solar system averages. Organic molecules like HCN may also carry isotopic peculiarities, suggesting variations in prebiotic chemistry. These observations could inform how life might emerge in environments with chemical signatures different from our own solar system. The implications are immense. Every molecule of 3I, Atlas could provide insights into the diversity of molecular evolution across time and space. As the Jupiter flyby approaches, all eyes are on the spacecraft and Earth-based observatories. Webb has already done its part, capturing unprecedented data, but the next few days could reveal additional clues. Will the comet release unexpected particles or exhibit outgassing patterns that challenge our models? Will instruments aboard Juno, JUICE, or Europa Clipper detect something new? Each observation adds to the story, bringing us closer to understanding this ancient visitor. In essence, 3I, Atlas is more than a comet. It is a time capsule, a direct physical sample of the early galaxy, carrying frozen memories of conditions that shaped star formation and chemical evolution billions of years ago. As it passes Jupiter and continues its journey, the measurements we've captured stand as humanity's only opportunity to read this message from the distant past. The Jupiter flyby is more than just a celestial event, it's a unique opportunity to observe 3I, Atlas under conditions that will never repeat. As the comet approaches, its nucleus begins to release volatiles more vigorously, driven by solar heating. This outgassing provides scientists with a rare window into the comet's composition beyond what infrared spectroscopy alone can reveal. Over the past 8 months, teams have meticulously measured methanol, HCN, CO2, OCS, methane, and water production rates. These gases originate from the outer layers of the nucleus, heated during the comet's solar passage. From these measurements, researchers concluded that 3I, Atlas formed in a colder, more carbon-rich environment than our solar system, a chemically distinct object with a story embedded in every molecule. But isotopes tell a deeper tale. Unlike surface abundances that fluctuate with heating, isotope ratios remain locked in from formation. The DH ratio in water, the 12C, 13C ratios in CO and CO2, and the 14N, 15N ratios in CN provide an intrinsic fingerprint of the object's origin. These measurements are not influenced by the comet's journey through interstellar space or its recent perihelion heating. They are fundamental properties, preserved across billions of years, offering a direct glimpse into pre-solar molecular cloud chemistry. By studying them, we gain insights into the Milky Way as it existed 10 to 12 billion years ago, a galaxy much younger, colder, and poorer in heavy elements than today. The flyby also allows astronomers to examine the physics of the comet in motion. Observations of outgassing jets, spin evolution, and orbital changes help refine models of cometary dynamics. Earlier, Avi Loeb had noted sideways pushes and unusual jet angles that contributed to anomaly scores. As more data arrives, the physics appears increasingly consistent with natural cometary behavior, leading Loeb to revise his rating downward. Nevertheless, he introduced the Trojan horse hypothesis, reminding the community that extreme ideas merit careful scientific consideration. A natural object carrying a passive payload is a theoretical possibility, highlighting how careful observation and rigorous measurement can address even the most speculative scenarios. The methanol enrichment is particularly intriguing. At 8% of total vapor, 4 times the solar system average, it reflects 3I, Atlas's unique formation environment. When combined with isotopic context, this enrichment suggests that chemistry in early, metal-poor regions of the galaxy was distinct from our own solar system. Organic molecules in 3I, Atlas may carry prebiotic implications, influencing how amino acids or other precursors polymerize. If these molecules indeed share the extreme DH enrichment observed in water, it could reveal pathways for chemical evolution that differ dramatically from Earth-based expectations. As 3I, Atlas passes Jupiter, scientists also watch for potential deployable objects or unusual particle emissions. While no one expects it to be a spacecraft, the object's passage through the Hill sphere offers a natural experiment, how a pristine interstellar object interacts with a giant planet's gravity and radiation environment. Instruments aboard Juno, JUICE, and Europa Clipper may detect subtle changes in particle flux or trace outgassing that could refine models of interstellar comet dynamics. Each observation complements the isotope measurements, deepening our understanding of the comet's origin, structure, and chemistry. Ultimately, 3I, Atlas is a messenger from the early galaxy. It has traveled billions of years, preserving isotopic fingerprints that capture temperatures, densities, chemical abundances, and radiation fields from a period predating our sun day. Its outgassing behavior, chemical composition, and isotopic ratios combine to form a comprehensive record of an era and environment otherwise inaccessible to direct observation. Humanity has never had the chance to study an object that traveled across the galaxy, carrying intact memories from the Milky Way's formative years, until now. The Flyby is not simply a visual spectacle or a curiosity, it is a measurement of cosmic time, a window into galactic history. By observing 3I, Atlas in real time, scientists are piecing together the story of the Milky Way's infancy, tracing chemical evolution, and understanding prestellar conditions that set the stage for star and planet formation. These insights have implications for everything from planetary science to the origins of life, extending the boundaries of what we know about the universe.